A body is traveling at 3 meters per second. It accelerates at 0.5 meters per second squared for 6 seconds. Calculate the distance covered. So we need to extract. We've got an initial velocity, we've got an acceleration, we've got a time, and we are interested in a distance. So we are going to say distance is equal to, or displacement is equal to ut plus a half at squared. Substituting in values, 3 times 6 plus a half, 0.5, and 6 squared. This is not going at a constant velocity, so I have to use an equation of motion, and I'll end up with 27 meters. That wasn't too bad. The diagram represents a displacement versus time graph for a trip made by a car. Now this is a classic shape for a velocity time graph, so people get all confused, but there's no reason to. The other thing that's weird about it is that the displacement is in kilometers and the time is in hours. So they say describe the motion from A to B. From A to B, we have got A, increasing displacement if you like, but we also have a solid gradient there that is increasing. It is a positive constant. So positive constant on a displacement time graph. The gradient is the velocity, change in displacement over change in time, and that is a positive constant velocity, as well as there is, if you've got a constant velocity, zero acceleration. Then B to C, there is no change in displacement. In other words, this object actually isn't moving at all. So there is zero velocity. And once again, zero acceleration. And finally, we are coming down here. We have got a negative, but again, it is a constant gradient. So constant velocity. And again, there is, because it's a constant velocity, zero acceleration. Now they ask me to draw a corresponding velocity time graph for this. Now, the first thing is I need to consider what is my velocity. My velocity is going to now be measured in kilometers per hour. If you went to meters per second, you made work for yourself. Nobody said you had to. And my time is again in hours. I've got a divider at 0.2 and another one at 0.6 and an end point at 0.8. From 0.2 to 0.6, I have a constant velocity. I can work out that gradient. It is equal to 10 divided by 0.2, which is going to be 50 kilometers per hour, and that is the gradient. Then from 0.2 to 0.6 is 0. There's no velocity, zero velocity. And finally, I find that over here I am going from 0 to 10, so it's negative 10, and again it's 0.2, so it is negative 50. And I have got, my graph looks like that. So this displacement turns into this velocity, that displacement turns into that velocity, and this displacement turns into this velocity. A ball bounces to a vertical height of 0.9 meters. When it has been dropped from a height of 1.8 meters, it rebounds immediately and the effects of air resistance are negligible. How long does it take the ball to hit the ground after it has been dropped? So it goes 1.8 meters. Let's see what information I've got. Through all of this, I'm definitely accelerating. I'm in free fall, so acceleration is equal to 9.8 meters per second squared down. I have traveled a displacement of 1.8 meters down. I was dropped. That means my initial velocity was 0 meters per second. And the question is how long? So if I'm looking for long, I'm looking for time. Therefore, I am going to say S is equal to UT plus a half AT squared. I have no initial velocity, a half of 9,8. They're interested in the time, and the distance is 1,8. And when I square root that, my time turns out to be 0,61 seconds. What speed does the ball strike the ground? So again, I'm going to take this information, but this time I'm going to substitute it into v squared equals u squared plus 2as. And I am going to say my final velocity I do not know. My initial velocity was 9,8 down. Let's go with negative. And 1,8 is the distance down. Sorry, that's 1,8. And therefore, when I square root that, I find that my final velocity becomes 5,94 meters per second. At what speed does the ball rebound from the ground? So in other words, I now need to find out what the initial velocity is of the second part of the trip. So the second part of the trip has a distance of 0,9 meters up, at least an acceleration of 9,8 meters per second squared down. I have a final velocity at the top of this projectile of 0. What is the initial velocity? So I'm going to go v squared equals u squared plus 2as. And I land up with 0 is equal to, I don't know the initial velocity of that bounce, 9,8 down and 0,9 up. One of those has to be in the opposite direction, and my initial velocity will turn out to be 4,2 meters per second. Then I have got, the last thing is how long does it take the ball to reach its maximum height after the bounce. Again, I'm going to be using this information over here, but I'm interested in time this time. So I'm going to go v is equal to u plus at. My final velocity is 0. My initial velocity, I do know, is 4,2, but it's 4,2 going up. So I'm going to leave that at positive, plus 9,8 meters per second squared down, so I need to change that to negative. If I had used s is equal to ut plus a half at squared, I would have landed up with a quadratic. So this is a better equation to use when I've got the information, and my time turns out to be equal to 0,43 seconds. In the circuit represented below, the battery has an internal resistance and an EMF, and we've been given a voltmeter. Calculate the resistance of the external circuit. This was absolutely pedestrian, so it's 1 over R parallel is equal to 1 over 6 plus 1 over 6, which is equal to 2 over 6. Invert R parallel is equal to 6 over 2, which is equal to 3 ohms. So I've reduced that to a 3 ohm resistor. Then the R external is equal to the 3 ohms over here, plus the 2 ohms over there, and that's going to be 5 ohms. Calculate the reading on the ammeter. So, what do I know? I do know that there is, on the main branch, that ammeter is on the main branch. This information is also on the main branch. So I can simply say that I is equal to V over R, 10 over 2 is 5 amps. Then I'm going to say calculate the internal resistance of that battery. So I'm going to first worry about what is the total resistance. R total is equal to the EMF divided by the series current. My EMF, I was told, is 30. My series current is 5, and I land up with 6 ohms. That is my altogether resistance. My external resistance I've just worked out earlier was 5 ohms. So R internal is equal to R total minus R external, and that is 6 minus 5, and that's 1 ohm. Try and give the examiner an opportunity to give you some part marks by showing your working. In the photo, the mixer, the microwave, and the iron are all connected to the same multiplug. And here is a circuit. Cool. The fuse blows when the current exceeds 15 amps. Okay, because all of that current would go through there. Calculate the resistance of the mixer. So the first thing I'm going to do is I'm going to say power, because I'm given the power of the mixer, 440. I'm given the potential difference of the mixer. So power is equal to V squared over R, and therefore I'm going to say 440 is equal to 220 squared divided by that resistance, and my resistance comes out at 110 ohms. A student then wishes to establish if all three appliances can be used simultaneously. Use applicable calculations to establish if the multiplug circuit will be able to run all three appliances at the same time. So I'm going to say power is equal to V times I. Power is 440. V is 220. And therefore I in the top branch is equal to 2 amps. I in the bottom branch is equal to 4 amps. Let's see what's going on in the middle branch. We've got 1,32 kilowatts, which is 1,320 watts. Power is equal to V times I. 1320 is equal to 220 multiplied by a current I do not know. And when I rearrange that, that current turns out to be 6 amps. So what have I got? I've got 2 amps on that branch, 6 amps on that branch, 4 amps on that branch. So altogether I have got 12 amps. 12 amps, you need to conclude, is less than 15 amps, therefore won't blow. Don't assume the examiner can add up your numbers for you. The iron is used for an average of 2 hours per day. What is the cost of the electricity used if the average cost per kilowatt hour is given as 116? So let's work that out. The first thing is power is equal to V times I, which is equal to 220 volts, times by the current on the iron is 4 amps, and that's 880 watts. Then I am saying that the energy used is equal to power times time. The power, I'm going to change the watts into kilowatts, 0,88. The time is, it's used for 2 hours per day, times 2, equals 1,76 kilowatt hours each day. They don't say per week, per month, per year over here. What is the cost if that is, over here they've said per day, so we're going to cost it out per day. And the cost is equal to 1,76 kilowatt hours multiplied by 116,63 cents, and that turns out to be 205,27 cents. If you left it like that, perfect. If you decided to change it into rands, that is also absolutely fine. In the circuit, in the sketch, water is heated using an immersion heater with a resistance of 40 ohms. When the switch is closed, there it is, for 50 seconds, that's the transfer to the water. The EMF of the battery is given and the internal resistance is given. What is the reading on V? V is across that 40 ohm resistor, and I've been given an energy for that 40 ohm resistor. So work done is equal to V squared T over R. 18,000 is equal to V squared, 50 seconds, divided by 40 ohms. When I rearrange that, V, not V squared, because I'm going to square root it, is equal to 120 volts. What is the reading on the ammeter? The ammeter is on the main branch of the circuit. I have got a parallel network over here. 1 over R parallel is equal to 1 over 60 plus 1 over 40. The lowest common denominator is 120, and I land up with 2 plus 3, which is equal to 5 over 120. Invert it because it was 1 over, and that is equal to 24 ohms. In other words, 120 divided by 5. So I've reduced that to a 24 ohm resistor. The next thing that I need to do is I need to say the current going through here. I know that the voltmeter reading across this branch, I just worked it out, so I'm able to say, when I regard this part of the circuit, I am able to say current is equal to V over R, 120 volts over 24 ohms, and that is going to give me the series current of 5 amps. It's the same at all points of the series circuit or over the whole parallel network. Finally, what is the resistance of R over here? So I'm now interested in this R there. I'm going to say R total is equal to the EMF divided by the series current, which is equal to 200 divided by 5, and that turns out to be equal to 40 ohms. But of those 40 ohms, I do know that some of them come from this 24 and some of them come from that 6. So R is equal to the 40 total less the 24 less the 6, and that leaves me with 10 ohms.